So, hey folks, welcome to my talk about SLOs, SLIs, and air budgets at scales. I first proposed this talk close to 2 years ago, and Jason was gracious enough to keep it on the schedule, even though throughout the past couple of years, we've had a new normal. Over that time, I've given variations of this talk in different online conferences, and I've learned a lot on the subject matter during that time. So I'm really pleased to be presenting the sum of my learnings over the past couple of years. This is kind of the greatest hits version of the previous talks that I've given on the subject. But first, I've got a little survey for folks. Raise your hand if you know what this graph is. Pete, is your hand up? Adrian, folks. Okay, if you know, you know. Raise your hand if you've used this in anger. All right, we've got some folks. So we all know we're here today in part because of this thing. If you don't know, that's okay, but we're going to come back to this. So hi, I'm Fred. I'm an observability engineer at Zendesk. Our COVID travel policy is still a little bit weird, so I'm here on my own to present this, which means that the opinions in this talk are my own, not my employer's. I've been working in monitoring the observability space for about as long as the graph on the previous slide. And I like to think about SLOs, air budgets, histogram, and I've got 2 young kids, so I'm definitely happy to get some of this great Portland coffee. Let's kick it off. So about 3 years ago, I took a new job at Zendesk, and because I've been focused on this relatively new thing called SLOs, I got tasked with a project to bring SLOs to an engineering organization with over 1,000 engineers. At the time, there was a big push to make the product as reliable as possible, so I needed to come up with a way to roll out SLOs and air budgets. And to do that, I really had to understand what SLOs and SLIs were programmatically, so I did some research. I started off with reading the basics. The SRE book, the SRE workbook. I know folks have seen Liz Fong Jones and Seth Vargo's Google Cloud presentation on SLOs. Great video. I'd given a number of SLO-related talks previously at a previous job, and one that you may have seen was called Latency SLOs Done Right, which was also presented by Theo Schlossnagel and Heinrich Hartmann. But even when I look back at that talk and watch it, I can spot the errors that I made in it. Subtle errors in the formulas and error here and there in the math. And what I really found researching this topic, that there wasn't a prescriptive equation for SLIs and SLOs as a formula. The Google books talked about SLIs, but were kind of vague on the subject. I mean, they had some formulas here and there, but they weren't that consistent. They had formulas for SLO, but when I dove into the details and tried to match them up, some of the times they had a time period, other times they didn't, so they were more abstract concepts. And a recent book, Implementing Service Level Objectives by Alex Hidalgo, actually had a phrase in there saying like, I'm not deliberately not being prescriptive, because each of these are going to vary depending on what your organization's needs are. So out of all these resources, I found Liz and Seth's video. They had some strongly prescriptive formulas in there, and so I took those and I started to use those as a base for what I was going to implement at Zendesk. And over the next few years, 2019 to even 2016 to 2022, I call it a Cambrian explosion. Haha. There was just a ton of material coming out. There's SLO Conf. Alex's book came out. Lots of conference material. And so as I moved along through the process, I implemented a lot of those resources. So I got to work on making formulas that would work across a large engineering org, and I didn't want a lot of room for creativity or variance, because in essence, these are math formulas. And for folks who've worked at large engineering organizations, they know that the whole entire organization doesn't always do things the same way. So, formulas for SLIs. This is what I came up with. I've got a few examples here. An SLI is basically a way to delineate good requests from bad requests. A couple examples. My 99th percentile homepage latency over 5 minutes would be less than 500 milliseconds. My homepage request could be served in less than 100 milliseconds. My homepage response code is not a fail whale. And each of these had common components that I parsed out. There's a metric identifier, a metric operator, and a metric value. And these are examples that humans can parse easily in their head, and that conveniently you can also implement in any one of the open source or commercial solutions for monitoring or observability. So I went with these as a starting point for SLIs, and they also mapped pretty well to Liz and Seth's video. An SLO. An SLO is the number of good requests divided by the number of bad requests over a time range. So these also, I used color coding to parse these out so folks could understand them. We have three components. A success objective, which folks know is 99% usually. We have your SLI, which is embedded in the middle of the SLO. And we have a time period. A few examples here. 99.95% of 99th percentile homepage latency over 5 minutes is less than 500 milliseconds over the trailing month. It's a little bit of a mouthful on that one. Similarly, you can do the same approach with response codes or individual homepage, individual service requests. I tend to favor the latter approach, measuring individual requests as events rather than taking aggregates over a time range, and I'll go into why on that a little bit later. And then how do you get an error budget from an SLO? Well, you just subtract the SLO from 1, subtract the success objective. So in this case, if I'm going for 99.95%, my error budget will be 0.05% of requests. And in this case, when I have 0.05% of requests that have not met that criteria, my error budget is considered exhausted, which is also known as an SLO breach. So the same type of parsing formula here. I've got an error budget component, I drop the SLI in the middle, and then I've got a period. And the nice thing about this is you can adjust the period as needed, up or down, and that will suit different stakeholders. You could have a 7-day period for engineering teams, you could have a 1-month period for say product managers, and you could have a once a quarter for executives. So you can take this same SLI and vary the time period, and now you've got SLOs for different stakeholders. And this is what I started to roll out across the organization. So to sum up what I've shown you so far, there's a few points on getting thousands of engineers on the same page for SLOs and error budgets. First, you need real-world examples. Most of the published books out there don't go into too much prescriptive detail and don't give you complete examples consistently, and you need to have those. Because we all know that engineers are kind of like lawyers. They're going to look at what you present, and they're going to try to poke holes in it. They're going to ask questions, look for edge cases. So you really need to have that simple and buttoned down. Second, present formulas for each of these entities, which can be parsed easily by humans and machines. And third, you've got to be really detailed and consistent. I see so many SLOs out there in the industry examples, which leave off the time period, which is a very important piece. You might say, well, the time range can be whatever you want, but then it's not an actual SLO or an error budget. Folks might say well, 99% of my requests are under 500 milliseconds. What time range is that? Is it over 5 minutes? Is it over a week? SLOs are about prioritizing engineering resources. So when your error budget is exhausted, you're almost past the time at which you need to focus on reliability. And so it's really important to pick that time range. This is a monitoring conference, so with monitors, a lot of us are used to time ranges like within a minute. If my error rate exceeds 1% within a minute, I've got problems. So SLOs are a little bit different. They're about longer term and categorizing the reliability service over something that defines customer happiness. So we've looked at some example SLOs that most engineers can parse and memorize, and which engineering managers and product managers can use to correlate user happiness with. In most cases, that happiness means that your service is available and that it's running fast. We can take the formulas I just showed and extend them to cover both conditions at once. So here's an example SLI, SLO, and error budget, which covers both latency and availability. So I'll break this down, and most of you probably already know what this stuff means. If the page result is not a 5 something something, fail well, or the GitHub unicorn, that request was considered to be a good request. and it's also served in under 100 milliseconds. That's our SLI, which we can add a success objective of 99.95% and a time range of 7 days to be evaluated on. Now, to get the error budget again, we subtract our success objective of 99.95% from 1, which gives us an error budget of 0.05%. So 0.05% of our requests can either be too slow or an error, or both. It's simple to understand, and as I mentioned, you can create multiple SLOs for different stakeholders just by extending the time range. Now, on the point of the success objective here, I have 99.95% listed, 3.5 nines. Realistically, this is what enterprise customers demand these days. This means that out of 1 million requests, you only get 500 requests that are too slow or return a fail well. At my day job, we had a highly revered engineering SVP named Jason Smale, so we called 99.95% Smale's number. If you're at scale, you should look to this number as your success objective. So at this point, we've got some example formulas for SLIs, SLOs, and error budgets that should be relatively easy for folks to understand and straightforward to implement with most tooling solutions out there, both open source and commercial. And you've got a metric name, metric operator, and a metric value, which you can map to queries in Graphite, Prometheus, Datadog, Circonus, any one of the multiple solutions out there, Honeycomb too. So of these components of latency and availability, availability is pretty much the easy one. Simple example is I've got a 500 response, often saying, sorry, a problem occurred. That's easy to measure. There are some differences of opinion, like should I have a 400 be an error? Well, I guess that depends. If you roll out a change and you see a huge spike in the 400s, you probably did something wrong. If you see a few intermittent measurements of 400 responses, the user's probably doing something wrong. Latency, however, is more difficult to get right at scale. And when I say get right, there are two aspects to that. Does your measurement have the right precision for your scale? That is, if I have 1 million user requests, can I generate a latency aggregate, which means I'm not leaving more than a few dozen users out? The other aspect is accuracy. Is my latency aggregate for an SLO or monitor actually correct? Like if I've got 99.95% and I measure 99.93, is it plus or minus 0.005? Is it plus or minus 0.001? What are those error bars? And like so many cases I've seen, the answer to both is no. And let's dive in. So back to this graph. What this is an RRD graph, and it measures network usage and calculates the 95th percentile over the certain time period. Now, back around the dot-com boom in 2000, these were heavily used. If you had a co-location, your network provider would say like, okay, I'm going to bill you, $1,000 a month, and you're going to get 5 megabits at 95th percentile, meaning that if you take all of the 5-minute slices in this data set, you sort those, and if the 95th percent slice was above 5 megabits, then you get an overage charge. I just remember that being a dreaded thought in my head running a colo. And this really, I think, popularized the approach of using percentiles, and which would be seen 10 years later in 2011 with the advent of the StatsD protocol developed by Etsy, which provides P95, P99, P90 as latency aggregation metrics. I wrote more about this in a blog post I published a few months ago. That's the link to it. This is a slide from an SLO presentation, Latency SLOs Done Right, that I gave at SRECon 2019. And it illustrates a common mistake. These are two different latency distribution profiles, which are meant to represent service nodes that are behaving differently. The blue distribution represents a bimodal latency profile with lower latencies than the single mode red latency distribution. Basically, this could be two web servers, one performing well in the blue and one performing not as well in the red. And if we average the P95 values that we derive from each of these distributions separately, we get an answer, of about 430 milliseconds. But if we combine the data sets and calculate the P95 of the composite data set, we get 230 milliseconds, an error of almost 100%. Now, most monitoring and observability tools out there will happily let you use an average function for percentiles generated from different hosts, nodes, or clusters. And if the distribution profiles are the same, you've got the same data in each, that works. But in the real world, that almost never happens. It's when your services are having issues. If you've got one node, say out of 100, that's behaving like the red node right there, that you're going to encounter errors with this approach. And that's a problem with percentiles. And when you encounter these errors, averaging percentiles is going to mask this. So try to avoid this mistake where possible. And a lot of it depends on your tooling and how you collect that latency data. So we should be avoiding using percentiles as a latency data source and instead collect latency measurements as histograms. These are 3 different histogram implementations. This is a talk images are from a talk I gave at SLOconf earlier this year. I think it was April, which feels like a year ago. 3 types of histogram data structures. The first on the left is the open histogram log linear format developed by Sarkonis, where a latency measurement is slotted into one bin, sometimes called a bucket. The middle image is, some folks might be familiar with, is the Prometheus cumulative histogram, which, if I've got a latency of 125 milliseconds, it's going to record an entry for each of those buckets, moving down towards 0. And the third is something I developed at Zendesk called an inverse cumulative histogram, which is an opposite approach to the cumulative histogram. You can implement any of these with most monitoring and observability tooling. And what I've shown here is how you can do that with metric tags. So let's take the first example with the open histogram. If I've got a measurement of 125 milliseconds, I can assign a metric tag. I can record that as a counter, and I can assign a metric tag to that saying, oh, the measurement was greater than 100 milliseconds, but less than 200. And the exact buckets will vary. Similarly, I can do that with the cumulative histogram. I'll have to assign tags like less than infinity, less than 1,000, all the way down. So the faster my requests with this approach for the cumulative histogram, the more tags it will have, which can become a cardinality issue. And that led me to derive this inverse cumulative structure where I'm assigning tags based on what the request is greater than. So if I have faster requests, I need less tags. And so that kind of solved the cardinality issue for me. So unless you're using a native histogram storage type, like with IronDB, I think there's a few other out there like Atlas or Argus from Netflix and Salesforce. There's some native data structures out there for a time series database that will actually store histogram data. If you don't have those, you could use this metric tag approach. Now, the approach I showed on the previous slide is what I would term as raw histograms, where we keep a count of samples for each bin for each time slice. And with that approach, we can sum up different latency bins across an arbitrary number of nodes and time windows. And we have, because we're summing up the raw data, or at least the counts, we have errors that are effectively 0. There's a few other approaches out there to histograms, such as sketches like the GK sketch, Datadog's DD sketch, and there's approximate histograms out there, such as T-digest, which stores approximates of distributions using centroids. I think there's a good talk on this tomorrow. I'm looking forward to seeing it. So these 2 charts I took from the circ-LLhist paper, which described the open histogram log linear format. And there's 2 different workloads here on the top and the bottom. And these, on the left, these represent error percentages for the workloads across quantile values. You'll see your P9, your P99, your P90 across the x-axis. So overall, you can see, the log linear histogram, the red one at the bottom, did really well, had really low errors. The other, the digest, I think guillotines is on there too, as HDR. and tdigest, those did fairly well also. But there's a detail that's not in these charts. If I'm just using this, any one of these data structures to record performance values for a single node over a single time period, you're going to get these types of errors which are bounded. And they work very well. However, when you start to use sketches and approximate histograms across multiple nodes and multiple time windows, the errors can become somewhat unbounded, and there's not a lot of information out there on just how unbounded. So it's a difficult question to answer, like what kind of errors you get there. So which is why I recommend just using raw histograms, which store the sample counts per bin, and you just avoid that problem entirely, ensuring that any of the aggregates you generate from them to use for SLOs, say if you want my P 99.95, will be as accurate as possible. So try to use raw histograms where possible to record latency data, and then use those to power your SLOs. And if I've got an SLI that says, or an SLO that says, I want 99.95% of my requests under 500 milliseconds, you can just use the 500 millisecond bin for this and count up all the requests. The math is really easy. The math for sketches and digests is more complicated. The interfaces abstract some of that out. But when you're using raw counts, the error, you can be relatively sure that the error is close to zero for very large, even small data sets, including very large data sets. You can get, arbitrarily high precision because you're taking a sum and you're essentially summing up all the samples under a certain threshold. It doesn't get much simpler than that. Now, one common question I've gotten about SLOs and air budgets is, okay, this sounds easy for a monolith, but how do I implement them across a distributed service architecture? Well, one approach is to use an SLO and an air budget for each service, and that includes third-party vendor services. The errors generated at the backend services, meaning towards, away from the request source, are additive to the middle tier and edge tier error budgets in SLO. So in this example, we have a third-party service which generates a 1% error rate, a backend service with a 0.1% error rate, and a mid and edge tier service, each that are generating their own 0.1% error rates, exclusive of any downstream generated errors. The backend service with a 1% error budget uses only 10% of the budget, but the mid-tier service, because it's accumulating errors from the backend services, has an error rate of 1.2%, and it exhausts its error budget. Just like the edge tier, which sees a cumulative error rate of 1.3%. And the goal of something like this is not to assign blame to different teams, it's to prioritize reliability work. In this case, the third-party service needs to have reliability work prioritized on it. And that could mean trying a different service, assigning a cache, or just putting engineering resources to it. And part of the reason why we want our data on this to be correct is because prioritizing engineering resources is expensive. And we want to know that when we're doing it, we're actually getting some value out of it. And that's it. Thanks, folks. I could take some questions.
Awesome. I think we've got some time for some questions. Any questions out there? I've never seen that spotlight on it. Anyone? Oh, here we go.
That's a cool concept, the multi-service SLO. How does that, can you say how that might roll up to an application? A bunch of underlying dependent microservices? And could that? Maybe I'm asking for too much.
So one approach is measuring the error rates. How would an approach like I showed on the previous slide with multiple error badges roll up to an application? So in this case, your application could be the mid-tier. You could measure error rates that are generated just from that application and construct your own error budget for that application and measure each of the downstream components. Or you could just measure the error rate coming out of that application via as measured from the edge tier. And that's one approach. And then you could say, hey, application team, you've exhausted your air budget, go figure it out. And then they could go look at each of those downstream pieces. I mean, so we like to, what I've evangelized is each team owning a service should have an air budget and an SLO. And it's on them to prioritize their own reliability work, if they're, say, approaching like 80% of their air budget used. Thank you.
Any other questions? Nothing. All right. Well, we are running just slightly ahead of schedule, which is great. So because of that, we'll start the next session. So we'll start a break right now. We'll start the next session at, let's see, 10:55. So we'll still kind of hold it to about a 30-hour break. Feel free to grab some coffee, check out sponsors, and then meet us back in here for 10:55, and we'll have our next speaker, Joy, this morning. Thanks, everyone.